Toastmasters. Today, I'm going to talk about a concept that changed the course of history over a century ago. It amazes people even today. It all started out with a then obscure man who worked in the Swiss Patent Office and who had a lot of time on his hands to think and perhaps daydream. The concept goes like this. We have a ball. Drop the ball straight down, come straight back up. Simple, not complex. Let's suppose now that we take our experiment to a railroad car. This on a flat, smooth piece of rail on a railroad bed that's been well landscaped so that the ride is smooth with constant speed. That's important. We'll talk about that later. Constant speed. If you're all with me on that railroad car, I drop the ball, straight down, straight up. Same results. Next, let's all do something different. We're going to take this half of the room and we're going to ask you to step off the railroad car on the side of the track. This half is still with me in the car. All of you are going to watch the railroad car, this group, the ball, and me go by at constant speed while I drop the ball. What will you see? This group will see the ball going straight down and straight up, as before. This group will see something different. This group is going to see the ball being dropped as we go by, but the car is moving. So the ball is not going to drop straight down and straight up. It's going to drop in a bit of a V path because the car is moving. Why is that? The fact is that this half of the group off the road car is seeing the same event as this half of the group, but from a different perspective, a different point of view. That concept is going to become very clear in just a few moments. The next thing we're going to do is we're going to change our ball for a light source. And we're going to repeat the same 3 experiments again. But we must remember that a century ago, the scientific community, after many experiments to measure the speed of light, became cognizant of the fact that the speed of light is constant in all frames of reference, which are moving at constant velocity with respect to each other, constant speed, or are stationary. So, sitting in the room here with a mirror on the floor, the pulse of light will go straight down to the mirror and come straight back up, just like the ball did. If we go to the railroad car, we get the same result. This pulse of light goes straight down to the mirror on the floor of the railroad car, moving at constant speed, straight back up. But when we do that 3rd experiment, some controversy will break out. The folks on the side of the railroad track are going to say, wait a minute. The light travels in the V path as we agreed upon before because the car is moving as the light goes down and straight back up. Light moves at 186,000 miles per second, or about 1 foot per nanosecond, but that is not infinite. As that light pulse is moving to the mirror there, the car is moving just a little bit, so there's a little bitty slight V path for this pulse of light. What does that mean? The people beside the track are going to say, wait a minute, we all agreed that the speed of light was constant, but it's faster. It looks faster from where we stand over here to you than it does to you here, despite the fact that we did the same experiments on the car and off the car, and got the same results. What's going on? That same problem occurred to that man in the Swiss Patent Office, Albert Einstein. After some considerable thought, he came to an interesting conclusion. The culprit is not that the speed of light is different. It's not. The culprit is not in how we did the experiment. It was done correctly. The culprit was in the clocks used to measure the elapsed time between the interval between the light going down and coming back up. What happened is that relative to the people off the track, the clocks for the people on the track run slower. Seriously? Yes. Relative to the people off the track, the people on the car, their clocks run slower by a little bit. Oh, really? Can that be proven? A century ago, the technology did not exist to measure time intervals of a few nanoseconds. By October 1971, it did. Two scientists, they named Hafele and Keating, procured several sets of atomic clocks, precisely synchronized, precisely calibrated. And they did the following experiment. One set of clocks they put in a naval observatory, which is on the East Coast. The second set they put in an airplane and traveled twice around the Earth to the west. Then they took the third set, they removed those set of clocks off the plane and put the third set of clocks on and went twice around the Earth to the east. It must have been a whale of a case of jet lag. One after another, and the experiment was over. Guess what? The time intervals measured by all three sets of the clocks differed from each other by the amount predicted by Einstein's theory of relativity. It was true. That's amazing. That concept, which is called time dilation, forms one of the central aspects of relativity theory. Relativity theory is much more complex and deep than what I described to you here, but that's one central tenet. There are more. Relativity touches many areas of engineering, science, and astronomy. It has enabled us, humanity, to understand much more about the world we live in, the universe in which we reside. It even formed the basis of that famous equation, E equals mc squared, that quiet man in the Swiss patent office used to formulate all of nuclear physics, theory of nuclear physics. Fellow Toastmasters, the next time you see someone playing with a ball, or handling a flashlight, or you see a railroad train going by, remember, this all started with a soft-spoken man who had time in his hands to think about the deep secrets of nature.